Yes.
Baldormero Olivera, which I call Toto, we were graduate students together, and we worked the late shift, which met all night, every night, 7 days a week for years. And I learned a lot from him, and hopefully he learned something from me. But one thing about him is really quite unique. He's from the Philippines. He was a graduate student at Caltech, and he wanted to do something in the Philippines, but he felt he shouldn't do what he could do in the United States. He should do something that was unique, and maybe something that only you could do in the Philippines. And so that led him into his investigation. But he didn't just worry about getting publications. He kept thinking about how can you use this? What value is it? And he's done a tremendous job.
Thank you. Okay. Thanks so much, Ron. What I'd like to leave you with is novel sources of drugs. So we need new sources of drugs. It turns out that the ocean is going to be a major source of drugs because the biodiversity there produces all kinds of compounds that people are just beginning to figure out. But more important than the biodiversity itself is that there's a lot of interactions between marine animals. And these interactions essentially leave behind a set of molecules that evolve in which one animal is trying to change the behavior of another animal. And it turns out that this is an almost unexplored source of drugs. And we happen to stumble on one interaction of that type. And so what I'd like to do is to tell you how this story evolved. And it also gives you some idea of why the scientists in this room all feel that basic research is extremely important in generating unexpected opportunities. And so this is a case study of that. Because we just wanted to understand these snails, which, as Ron said, I'm from the Philippines, and there are a lot of them. And these snails are very specialized. So the one in the middle will only eat fish, nothing else. The one on its right will eat certain types of marine worms, and the one below that will only eat other snails. And all of these snails are venomous, like snakes, and they inject venom into their prey. And it turns out the venom is very complex, typically with between 100 and 200 different components, and those components all target a specific molecular target, usually an ion channel, a receptor, or a transporter. So I'd like to tell you about one of these snails in particular. So this just shows you how a typical fish hunting cone snail catches fish. When it sniffs a fish, it extends its proboscis, and this is real time now, and it's going to strike the fish with its proboscis, and you're going to see what happens. And you can see that in a few seconds, the fish is immobilized, and now the snail completely consumes it. So this is what a fish hunting cone snail does. Okay. And there are about 50 species that hunt fish in this particular way. And what they do is when they touch fish skin, a disposable harpoon-like tooth comes out, and you can see it's shaped like a harpoon. And once it pierces the fish skin, you can see that it's highly barbed. And so the fish is tethered. And so the fish essentially has been harpooned mechanically. But at the same time, that tooth is hollow. So it functions as a disposable hypodermic needle. And so you could say that 50 million years ago, this group of snails got their start because they essentially evolved a drug delivery device, the equivalent of disposable hypodermic needles that they just discard after every use. So there is a quiver-like organ called the radula sac, where 40 to 50 harpoons are stored in various stages of assembly. And when the snail goes hunting, it moves one harpoon to its proboscis, and the long tube is the venom gland where the venom is made, and it's attached to a venom bulb that pushes the venom out. The species I want to talk to you about is the species we first studied, and the reason was that this snail kills people. And 70% of people who get stung by this snail die in the absence of medical intervention. And so when we started working on this snail, we really wanted to answer a very basic scientific question, which is, why does the snail kill people? And so if you want to do a project like that, first of all, you have to have a lot of starting material to be able to pull out the compound in the mixture that actually kills people. But our other problem was we had to develop an assay. And it's not completely clear what kind of assay you should use if what you're interested in is what kills people. But if you read the medical literature, it turns out that people probably died because their diaphragms got paralyzed and they couldn't breathe. And so we decided to do a paralytic assay. And I'm very proud of this slide because it literally was the only equipment we had in the Philippines at the time. And I came from the Stanford biochemistry department as a postdoc, which had a lot of equipment. And this is the assay we used. We would put a mouse upside down on a wire screen and inject various fractions of the venom. And the mice can stay on the screen as long as they want. But when they started to get paralyzed, if there was a paralytic component in that fraction, then their little paws would start to get paralyzed and they couldn't hang on and they would fall. And so we called this falling time assay. And so we had, okay. So that's the assay we used. What we ended up with were the two compounds that I believe kill people. So there are 100 compounds in this venom, but these are the two that probably kill people. One of them, so these are very small protein-like molecules called peptides. So proteins have hundreds of amino acids. And so if you have your regular protein, you have a sequence of 100 letters. But as you can see, the one on top only has 13 letters, extremely small. And it turns out that that component acts very much like what you have in cobra venom. So when you get bitten by cobra, you can't move anymore because cobra toxin will essentially block communication between nerve and muscle. And that little peptide does exactly the same thing, except it's much smaller. But there was a second component that was also paralytic, and it turns out that that acts by the same mechanism that makes pufferfish such an expensive fish to eat in Japan, right? Because if you order pufferfish, it's very expensive, not because the fish is rare, because they're really very common, but because if the chef doesn't know what they're doing, the customers begin to drop dead. And the reason, of course, is that at certain times of the year, pufferfish have a deadly toxin, fugu, called tetrodotoxin. So how did we purify these? And the breakthrough really was that an undergraduate at Utah, Craig Clark, told us that what we were doing was all wrong, that we were injecting mice IP, and he said, you should inject mice directly into their central nervous system. And so what I'm showing you are the components of the venom separated. And what you can see is that some of them cause paralysis. Some make mice jump and twist as they're jumping. Some make mice uncoordinated. Some put mice to sleep. Some make their back legs drag. Some run around in circles. Some swing their heads back and forth. And so every component causes mice to do something different. And that was really the breakthrough in our research, because now we could purify every component by just following what they did. And so Craig recruited other undergraduates, and this young man decided to look at this snail and used Craig's assay, essentially injected mice directly in the central nervous system, and he purified a peptide that made mice shake. And so why am I telling you this? Because today, that peptide is a commercial drug for intractable pain. So it's FDA approved, and this is its structure that Michael McIntosh determined. And when morphine doesn't work anymore, when patients become tolerant to morphine, this is one of the alternatives that may work. So in very severe intractable pain, this peptide is what works. Now, what I'd like to show you is that Conus geographus has an entirely different way of catching fish. It doesn't stick its proboscis out when it smells a fish. What it does is it opens its mouth, it approaches the fish, it releases some components of its venom, and what you're going to see is that, curiously, the fish doesn't swim away. And so what you're seeing is that the snail is going to completely engulf the fish, and it has a very, very big mouth. And curiously, the fish is just completely engulfed. And only after it's completely engulfed does the snail sting and inject its venom. So you're going to see it when it stings, because the fish is going to jerk. There we go. And so the fish struggles and then becomes paralyzed. So this is a different strategy for catching fish. We call this the net hunting strategy. And what we think happens is the snail releases components of its venom that make the fish a little lethargic, easier to capture. We call those groups of peptides the nirvana cabal, because the fish are all spaced out. And what we've done is we've studied the components that make the fish hypoactive. And among other things that the snail releases is insulin, so that the fish is not only without sensory input, but is also hypoglycemic with very low glucose. And so one of the peptides that we're excited about, which is part of the nirvana cabal, has reached phase 1 human clinical trials for epilepsy, intractable epilepsy. But the one probably of more interest here is a peptide shown on top, a small peptide that's very promising for intractable pain and seems to be even better than the first peptide I told you about. So from this one interaction, studying the interaction between one snail and its prey, this has been the unexpected outcome. An insulin, which may have applications for type 2 diabetes, 2 compounds that are in phase 1 human clinical trials for intractable cancer pain and for epilepsy, and finally, these studies led to the development of a drug that is approved. So you can see that there's potential for studying these interactions, and they're very understudied. So what I'd like to close with is to just let you know, when you know the behavior of the snails in situ, you find all kinds of surprises. So we had 5 fish in the aquarium, and 2 of them disappeared overnight. And so we had a night cam, and I'll show you what happened, because it was very unexpected. We only took this recently. And if you look carefully, one of these fish looks a little punky. You can see it doesn't swim as well as the others. And look, it's right by the snail, and the snail just glopped it up. So we thought, okay, that's a coincidence. But then, 3 hours later, there was a fish that looked really abnormal. And so the snail, by releasing venom components, is getting the fish to do this. We call this particular video the final pirouette. But then the amazing thing is what you'll see next. That fish goes straight for the mouth of the snail on its own. So there's a lot of stuff we don't understand about this one snail, which is probably the most well-studied snail and its prey. But what I want to end up with is to tell you that although there are 800 types of cone snails, they are a very minor fraction of the total venomous biodiversity in the ocean. And there are two other groups, turids and auger snails. And it is the turids that are really the major biodiversity with 12,000 species. All of them are venomous. Their venoms have over 100 different components, just like Conus geographus. And for this occasion, what I would like to do is give you some turids to take home, because in fact, that is the future of drug discovery. And there has been a breakthrough because we could never study turids, and part of the reason is that they're extremely small. And so in the old days, you just couldn't do any work with them. But there has been a breakthrough to be able to get these small guys that live in deep water. And this fisherman is part of the breakthrough. So not all breakthroughs have to be high tech. This is the lowest tech breakthrough that you'll ever see. So this fisherman is bringing a rope up to the boat, and the guys are going to pull up this rope, and at the other end of the rope are old fishing nets that they tied together, that they dropped in the water 5 months earlier. Why are the fishermen doing this? Because the Japanese love to give their kids little microscopes, and they want them to look at natural history objects. And so they're always coming to the Philippines asking the fishermen to find microscopic shells like this that people can look at under the microscope. If you've ever tried to find a microscopic shell, it's a pain. And so the fishermen figured out how to do this efficiently. All they do is tie these old nets. You can see this is very high tech. And the net, there it is, has become an ecosystem. And it's been colonized by larvae that are swimming around. And so now all the fishermen have to do is bring up the net and shake it on a mat, and out come a whole bunch of shells like this. And what we found, we did a census of this net, and what we found is that this net, which has, you can see that's 1 centimeter. These are adult snails, they don't get any bigger, is that out of the 606 snails in that net, there were 155 different kinds. And what was more significant was out of the 155, 36 were venomous, including turids. So 1 out of every 5 is venomous. And so in your little packet, you're going to have a little biodiversity of the ocean. This is going to be handed out during the reception. Look at it under a magnifying glass. 1 out of every 5 of the different snails there is a venomous snail that contains 100 bioactive peptides, components that we hope someday will be made into drugs. And so on that note, I'd like to show you just what the snails look like when you magnify them. So take one of these during the reception. We'll have them out there. It's yours to take. And do look at it under a microscope. And thank you very much for your attention.
So I did say that you would see something you've never seen before. I hope that that's true. So the excitement continues. Our next speaker is a Nobel laureate, Mario Capecchi from the University of Utah. We're very honored to have him here, and Ron will introduce him further.
My other friend from the University of Utah is Mario Capecchi, and I love talking to him. Always learn some new stuff, and I think you should be very interested in what he's going to have to say. This, or do you want to talk?
If this is good?